Thank you. I'm honored to be here talking something, frankly, it's only indirectly related to large-scale databases, which is how I want to see us evolve and how we build applications on the cloud. And I would say what's going on is we're kind of in this big transition from obviously things that were essentially on-prem and in our own data centers to virtual machines in the cloud, which are really a kind of a machine abstraction. And to the part I think that's interesting now, which is what are the application abstractions we can have instead of machine abstractions. So that's what we're talking about today. And so now we're taking the resources for granted in some sense, the elasticity that was talked about earlier, right? So there are really essentially as many resources as you want. You're in an environment of services, not of machines. And in this environment, what you think of for your own applications is the services that you want to build and how they relate to these other services, right? I don't really want you to think about the libraries and the OS and the pieces on the machine. They're really not that relevant anymore. And finally, all this is in an environment where you're expected to deliver high availability. And so a lot of the actual challenge is how do we evolve systems and keep them up? Right? If we didn't have to evolve them, it would be really easy. Right? That's kind of the ATM model. ATMs haven't changed in roughly 30 years. They're really pretty easy to keep up. But we want to change stuff every day, and doing so is highly risky. So at the base of this is something called containers. I'm going to talk about what this is, what I mean by the term. It turns out Google's been using containers essentially since the beginning of Google. And they're just packages for delivering applications. I'll talk about it more in a minute. But essentially, all of the things that Google does are run inside containers. And so this is our mechanism for managing applications, and it's quite different than the mechanism of virtual machines for managing applications. Right? And the historical reason for that actually is that Google and virtual machines, at least the modern version of virtual machines that came out of Stanford, in fact, those are essentially of equal age. Right, so that was not a tool for Inc2Me when I did this the first time around. It's not a tool for Google when it started. Now, I want to clarify the key differences here. So first thing is, for a virtual machine, you're essentially sharing at the machine level, which means that the physical machine is shared with potentially other customers, but what you have that's private is your own, essentially, OS, libraries, and user code. And that's all right. In the container model, where I'd like to get, and we're partially here but not completely, is essentially what you share is the operating system and below, and what's private to you is only the stuff that's relevant for your application, which is essentially the libraries you need and the user code that you have. Now, an important difference here is that what is the interface at which you interact with the system? And for virtual machines, it's by definition the x86 ISA, which I'll point out is a very low-level interface, right? But that's what you're given as a primitive tool. And in the container world, the right interface to think of is really the syscall boundary, right? So this is actually quite important. What it means in particular is that there's fundamentally less overhead in this model. For example, virtual machines, although they might have low switching costs for virtualizing instructions, they have high costs in terms of networking and I/O, and in particular in memory. A virtual machine needs a fairly large amount of memory just to exist, because it's actually running two operating systems on the machine. You have an operating system that's running the virtualization, and then you have your own guest operating system inside, right? And they actually use essentially independent RAM. And the containers is really one OS, right? And it's much less virtualized. We'll talk about that. That's really more the direction, I would say. We'll get back to that in a minute. I also view this as enabling more magic, and this is a little bit more subtle. What I mean by this is that if we see your application at the syscall boundary, then we can tell, are you blocked on I/O? Are you under memory pressure? What's going on with your application that we might be able to help with? If we see only the x86 instructions, it's actually very hard to tell what the application's doing. In fact, in general, you can't even tell if the application's spinning or blocked. Right? Now, there's ways to fix that. You can, or for example, another one is, can you tell if it's an application starving for memory? Easy to tell with syscall boundary, hard to tell with x86 boundary, right? You can cheat and put in what's called a balloon driver, which is kind of an agent inside the guest OS to tell you what's going on with virtual memory. But that's an inference mechanism, and it's lossy. And by the way, it only tells you about virtual memory. It doesn't tell you about anything else, right? You can think about the OS and containers as being our super agent that knows everything your application is trying to do and can help us on your behalf. So a lot of what's important about this is that by knowing what you're trying to do, we can help you in terms of giving you more memory, in terms of auto-scaling the number of nodes you might need. So that's the difference. Another complication is really two kinds of containers in the containers discussion right now. And I want to distinguish them because they're both important, but they're a little bit different. The one that's popular is Docker, which is really about containers as a mechanism for packaging. What I mean by that is you control exactly the versions of libraries you want to use, and your app and those libraries get deployed together, which means you don't have the kind of the DLL hell. Right? It really means that what you run on your laptop runs the same way on the cloud because it's got the same dependencies. Right? That's a very useful thing. You can kind of fake it with static linking, which is an awkward way to do it. Docker is a much nicer way to do it. Linux containers are actually about performance isolation. This is the part Google's invested in the last 10 years. In fact, a lot of the code in Linux on performance isolation for containers came from Google. It was upstreamed. And I call performance isolation to say the purpose here is to run two processes next to each other where if one goes haywire, it doesn't mess up the other one. For example, it doesn't use all the memory, doesn't use all the bandwidth. So it's actually trying to get some independence of performance. And this is actually quite sophisticated now. You can actually have nested groups of containers. For example, you might give a little bit of memory to your logging agent so that it can do logging, but the logging agent will never kill the primary container, which is your application. That's a good use of performance isolation. So both of these kinds of containers are in play, and what's going on is we're kind of merging the two. So the modern container, when I say container, what I really mean is it's a packaging which gives you repeatability of what you deploy, and it's a performance isolation mechanism so that you can run multiple containers on the same physical hardware with limited interference. It is not a security boundary, although that's an open question whether it could be or not. It is much easier to secure the x86 boundary because it's comparatively narrow and very stable, although more complicated than it should be. The syscall boundary is wide and relatively unstable by comparison, and therefore harder to make secure. So at the moment, Google uses virtual machines for a security boundary and containers for performance boundary. But that still gives us better utilization because we can actually decide how we want to run jobs on the same machine. When we use our internal jobs, things like the search engine, we don't actually use virtual machines at all. The containers run directly on bare metal, and that's because Gmail trusts search, right? So we're not trying to get a security boundary among our own applications. And likewise, a customer running on cloud could have two of their containers on the same virtual machine. We just wouldn't mix them with other customers. So Google has an interesting cloud offering in this context, which is we started with Google App Engine, which basically you can think of as a very high-level platform that takes advantage of language-level knowledge, Java or Python or Go. And so you write applications in App Engine, what you're really writing is kind of the core of, say, of a website. And then App Engine will scale that core to as many servers as you want dynamically. It actually makes it very easy to write scalable services for the narrowish domain of web services. For example, Snapchat, which is quite large, is implemented almost entirely at App Engine level, and they have essentially no operations people, right? Because all the operations is done essentially by Google to manage the virtual machines, do all the scaling based on load. So it's quite easy for them to build Snapchat because they're really only building the meat of the application. So that's a wonderful world if you can get there. The bottom GCE is like AWS in the sense that it's really about virtual machines. And so you can get virtual machines, you can put your own OS on them, fairly normal thing. What's interesting is this middle space, that's what I'm excited about, which is what I think of, you can kind of think of it as the process level of sharing. And we've done this, no slide. Back. There's a magic button. Don't press that magic button. So Kubernetes essentially is an open source project which is managing things at this container level, which I'll talk about in a second. GKE is the hosted version of that, where we'll manage your containers for you, but you can run it on-prem using Kubernetes because it's open source. And what I want to point out about this is this middle layer is in some sense the sweet spot. It's almost as flexible as virtual machines in that you can run many, many different kinds of loads in any language you want. But it's easier, it's more flexible than App Engine, where App Engine is really good if you want to build a website, but if you want to build a mobile backend or batch processing, right, it wouldn't be a good fit. So this is kind of the sweet spot of ease of use and flexibility. So what is Kubernetes? Well, if we do it right, what I want you to think about when you're using it is the composition of your services, how the load balancing works among them, the names of the services, the state management, monitoring and logging, and kind of upgrading. These are kinds of application level things you're thinking about. What you don't worry about in Kubernetes done well is the OS details. So for example, you shouldn't have to patch your OS. Right? In fact, we know most customers don't patch their OS correctly. And in fact, it's bad for the whole world that people are responsible for patching their own OS, right? Because a huge number of sites are vulnerable from that. So if you're using the container level thing, we should be able to patch the OS for you, and that is what we already do for App Engine. You don't worry about packages and conflict. If you want to use a library and another person in your same group wants to use a different version of the same library, that's fine, right? We can actually put two different versions of the same library in the same machine. You don't worry that much about how big your instance should be, right? You don't have containers. You can kind of decouple the size of the machine you're using from the application, right? And late bind that quite easily. You don't worry about mixing languages, and you don't worry about port conflicts. I'll talk about both of those in a minute. All right. And the value of Kubernetes over just containers is that, as I mentioned, the hard part here is high availability in the presence of evolution. Right? So what we want to do is get to a state where you have a long-lived service that is evolvable and yet still highly available. And the mechanism of this is essentially building your apps as independent microservices. So you could think of a microservice as being kind of like the ideal object in an object-oriented language. It has state inside, it has an encapsulated boundary, which is its API. And the reason it's a bit better than a traditional object is that it's persistent. It's a long-lived object, even in the presence of faults. All right, so that's a fantastic building block. It's also language agnostic, which means you can have different services in the same app written in different languages, and we do that all the time. Right, so the nature of our APIs is that they are language agnostic. It also, in practice, means you can have a mixture of teams, because the reason we use multiple languages, frankly, is because we hire the programmers we can hire. And they know different languages, and they use their favorite language for their part of the system. And so, in fact, some teams are Java teams, and some teams are Go teams, and some teams are Python teams, some teams are C++ teams. Right? And in this model, the service boundary is also essentially the team boundary and the language boundary. And that ends up making all the teams have higher velocity. And of course, the key to this, especially for high availability, is that a service has to be this long-lived thing. And so what is a service actually? And I would say the only thing that matters is that a service is a long-lived name. Right? The name has to survive essentially forever. And what it maps to changes over time. That's the key is we're going to remap the same name to many different implementations over time. And what Kubernetes does essentially is make sure that the traffic you have goes to the right version or even can be split among multiple versions. Now, I mentioned that we're trying to get some velocity out of this, and a lot of this comes down to essentially managing your dependencies, because it's the dependencies that end up reducing your velocity. So I'll give you a couple levels of dependency management. The containers themselves are an innovation in dependency management. This part is really the Docker part. And in particular, I have these two containers, my service and MySQL, they both use Python and glibc, but they happen to need different versions, right? This is kind of a mess. And in fact, what Google did internally was we actually forced all of our teams to use the same versions of all the key libraries. And if they didn't like that, too bad, right? It's not that good an answer. This answer is better. You pick the versions that you need because of other weird dependencies you have, and then we will make sure they don't interfere with each other. So that's what the first level container is giving you. We introduced in Kubernetes a new kind of boundary, which is called a pod, and this is the boundary of co-location. What I mean by that is containers in a pod will always be on the same virtual machine, which means they can share volumes, they can do IPC, they can do anything that co-located processes could do. Right? It also means if we migrate them, which we do, we will migrate the whole pod. Right? So that means dependencies within containers that you care about, you manage them by putting them in a pod. And the pod then keeps them together. A very subtle advantage of this is that the pod is also the unit of IP address allocation. And what that means is when you have a pod, you know that whatever port you want to use, it's guaranteed to be free, which is not true for containers in general because containers, we run several containers per machine. In theory, they may have conflicts over ports. Right? In fact, they do. And the way Google fixes internally, which again is not as good, is to essentially dynamically allocate ports so there'll never be a conflict. And that works, but it means you have to then tell all the clients what the port is, which in turn means you can't use DNS, because DNS doesn't distribute port numbers. Right? So by making this change, which is the pod is the IP address, now the ports are free. You can have whatever port you want. DNS works just the way it always did, so legacy stuff is very easy to put into pods. If you want port 80, you can have port 80. All right, so that's kind of two different ways of managing dependencies to make it easier to deploy stuff. And the third layer of dependency management is the service itself. And this is, in some sense, the most important. So in addition to each pod having an IP address, the service itself has an IP address, and it has a long-lived name. But now that name could be a DNS name. Right? So DNS can map from a name to an IP address. Every service essentially has its own load balancer, conceptually. And so you send traffic to the IP of the port, IP of the service. It will load balance among the pods. Right? And if you change the number of pods, the load balancer will adjust. I'll show that in a little bit. There's a few other things it does. It'll auto-restart pods that die. That just makes it easier to operate a service. But from the outside, what this means is that if you want to have a pool of services, all you need to know is the DNS name of the service and not the members. Right? You don't know anything else. And the membership can change. And in fact, we can change all the pods in a service just fine because the load balancer will hide those transitions. Right? They are decoupled from the clients. Now, I'm going to finish up on kind of pulling this all together with an example that you can't really do as cleanly as this any other way that I know of, which is, I said I want to get evolution and availability. So that means I need to be able to do some kind of rolling upgrade of a service. So I'm going to walk through how you do rolling upgrade using Kubernetes. I have to introduce two new concepts. One concept is the label. A label is just a piece of metadata you can attach to any object. So in this picture, you'll see there are, so I have a laser pointer. So front end is a label. So pods have these labels on them. You can make whatever labels you want. They're arbitrary. You can say, I want a label for this is European data, or this is my secondary or my primary, or whatever you want, right? You can add your own. In this case, we have first a label called front end, and what that means is that is the set of pods across which we load balance traffic. So you don't actually configure the load balancer. This is very subtle. What you do is you label the pods that you want to get traffic, and all the pods that have that label will get traffic. Right? So the load balancer is essentially listening for changes in labels, and when it sees that there's a new pod with the label front end, it will start sending it traffic. Likewise, if you take the label front end off of a pod, which you can do, it will stop getting traffic. That turns out to be really handy. For example, if one of your nodes is flaky and you want to debug it, you don't kill it, you just take the label off. And now it doesn't get any traffic, but it's still there, it's still alive. You can send it test traffic, you can log into it, debug it, whatever you want. Right? So we're decoupled whether the node is alive from whether or not it's getting traffic. And there is no direct configuration of the front end. Right? It's only indirect via labels. That's very important. It's very robust that way, you'll see. Second concept I need to introduce is a replication controller, which is this thing here. And it says its job is to make sure there's exactly k of a given pod. So in this case, k is 4. So it says, I want to make sure there's exactly 4 pods that have the label v1.2. Right? So here's our v1.2 label. So at the moment, this replication controller is doing its job. There are 4 of them. But if one dies, it's going to make a new one. And it makes a new one by essentially taking the 1.2 pod template and instantiating a new pod, which, by the way, no state in it. But we'll come back to that in Q&A probably. All right, so the way I do a rolling upgrade is I say, oh, I want to go to version 1.3. I will make a replication controller for the new version. I'll give it one node. Well, there aren't any right now, so it has to create one. It creates one with the new label 1.3. It's labeled front end, so what happens next? Gets traffic, right? Because that label gets detected by the front end. So now I have 5 replicas serving the traffic. And what I'm going to do now is start to take down the previous one. So I'm going to change the number of replicas down to 3. I have 4, I want 3. We'll get rid of one. Right? Replication controller kills that pod to get rid of it. Same thing over there. I'm going to go back on this side now. Change that from 1 to 2. Create a pod. It's labeled. And it gets traffic. All right? You can see how this is going to work. Right? So at all times here, I have essentially at least 4 pods. And I'm just changing these 2 counters. So I'm declaring how many I want of each one, and the system is reacting to that declaration and making it true. That's the basic way Kubernetes operates, which is it has a spec of what's supposed to happen, a status of what's actually happened, and it reconciles the 2. We call that reconciliation. So we can go to 3, go to 4, and eventually we go to 0 on the old version. And it kills the final version. Now at this point, we're completely on the new version. We didn't have any downtime. We didn't have any reduction in load capacity. By the way, which is a very cloud thing, because I didn't upgrade these nodes by changing the nodes. I upgraded these nodes by making 4 new nodes, 4 new pods running the new version with potentially new resources. So once you have elasticity, there's no reason to upgrade nodes in place. That's very risky and hard to undo. So we're always upgrading nodes by making new nodes that take the traffic and then deleting the old pods. We keep the old version around for a while because we may need to back this up. So in fact, the replication controller for the first old version doesn't go away by itself. You have to eventually get rid of it if you care. But because it's around, we could actually revert and go back to version 1.2 if we say version 1.3 has some flaw. All right, so I'm going to wrap up and then take some questions. So I feel like this is the world I want us to be in for how you write applications on the cloud. The level of thinking is at the level of services and not at the level of machines. And we make it easier, I think, to build applications this way. The services really are independent in the sense that they're only connected by their DNS name and the load balancer. So it's very easy to independently upgrade the services. It's also independent to scale the number of pods per service. So none of the clients know how many pods are actually implementing a service, and that's good. We don't want them to know because we want to be able to change that easily. Finally, the pods are an important building block. They're the template of a pod, of a unit of service. They can manage the dependencies for everything needed inside one node of that service. And because they have their own IP address, they're easy to migrate and they're easy to allocate ports on. Right? So they clean up a whole bunch of stuff. And in general, these container-based approaches really simplify development and deployment. So if you're using anything that's like script-like Chef or Puppet or Ansible, those are great tools for kind of building your systems from scratch, but they're very fragile. Right? This model is much more robust. You kind of decide on your dependencies externally, essentially statically, and then you deploy them having tested exactly what you deploy. Right? So very clean and robust that way. All right, I have about 9 minutes left. I'm happy to take questions. There's a lot of stuff in here. And I didn't actually talk about some of the things you might care about. And I can repeat the question if you don't want to get up. All right, thank you.
So pods and state. If you've got, I don't know, a database, it's got 1,000 partitions. You'd like those partitions to be dealing with, would you have one pod that, 1,000 copies of the same pod, or would you have 1,000 pods, each of which manages its own partition? And where does it get its data from? Does it store it locally, or does it store it from, get it from GFS or whatever? And how do you ensure that you get the performance benefits of accessing local data without,
So the short version is Kubernetes does only an okay job of state management so far. There are two common ways it's used. The first way it's used is with essentially network-attached storage. So in fact, a pod does actually have shared volumes that are mounted. Those are not typically on local disk, although they can be cached locally. The advantage of that is that when we migrate a pod, its local storage migrates with it, because it's in fact not local. It's essentially iSCSI underneath. That's one approach, and you can do that now, and that works pretty well. Another approach, of course, is to use storage services, which I think is not the right answer for this crowd, since you care about storage more than usual. But most users actually will have their storage in something like Bigtable or Google Cloud Storage. And since those are global services, you can just have each pod do all the accesses directly. And then the pods themselves are essentially stateless front ends or caches for the back-end storage systems. But to answer your real question, if you wanted to build a storage system using Kubernetes and you wanted to have 1,000 partitions, which we haven't done. We've done, tens of partitions, I would say. The way you do it is you use the network-attached storage or flash. You can use local SSD, by the way. Then you can't migrate. Well, you can't migrate easily or quickly, but you can migrate. But you can use local SSD if you want. Let's assume you're using local SSD because you want a high-performance storage node. If there are partitions, meaning that each of their data is different, then you actually have a replication controller for each partition. And its job is to make sure that you have exactly K copies of that partition, where K could be 1 or 2 or 3 typically. Right? So it will actually deal with making sure that you have multiple pods, but when the pod comes up, it's going to have to figure out how to get the data for that partition, which we don't solve. Right? We don't make it any harder, but we don't solve it. But we will know which partition it belongs to because it'll have a label on it. So it can say, oh, I'm partition 42. I need to get the raw data for partition 42. So Replication Controller will keep the right number alive, and we'll do health checking, a few other things like that. You then have to have some other mechanism to actually route your traffic to the right partition. So we don't help with that either, although we don't make it any harder. And so I would say, and you can use the pod IP addresses directly. So although we tend to, I don't know if I'd make a service for every single partition. That is an option, but I probably wouldn't. I'd probably just have one service for all 1,000 partitions. But you can know the other pod's IP addresses. But then if you lose a pod, you have to actually have your own mechanism to get the new address for that, although you could use DNS, or we use etcd basically as essentially a store for metadata. That's how we store the labels, for example. So you could definitely build this, but it's a bit more artisanal than I would like it to be. That is something that's going to evolve over time, though. And people are doing that now, but again, it's much better if you're stateless. If you want to manage your state, it's still a little crufty, but it's totally doable. It's just you don't get all the things I'd love to have. All right. Other questions?
Hi, maybe this is a detail, but I feel like I'm missing something, or maybe you need to explain more. The rolling upgrade for your replication controller started with 4 replicas with the older version. How did that first replica on the new version get created?
By creating a replica controller for version 1.3 and telling it to have one node.
And how did it know what to put in that node? Because it's starting with 0. The old the old controller has its own copies.
I didn't really say that. So when you have a replication controller, it's given the source of a pod as a template. So you can think of a replication controller as something that rubber stamps pods copied off the template. So the template was the version 1.3 container. And so that replication controller was always making version 1.3 pods that are all identical. Right? They can become unidentical after they start, but they always start identical from the template. Which we found, by the way, to be a very robust way to do deployment, because once you get the template right, then all of them are the same. Right? So we don't do any kind of scripts where you customize the pod after you start it. That just doesn't work very well. Right, so you do all your scripts statically to build the container that's the template, and then you just replicate that template. Because again, if anytime you need to restart a pod because it failed, if you restart from the template, then you get this guarantee that they're all still the same, which is, I think, what you want for robust systems.
Any other questions? Okay, Fabrice?
Yeah, I knew there'd be questions, so I kind of did a shorter talk in my slot, because there's a lot of stuff here.
Hello, yeah, I've seen that Kubernetes is often associated with Mesos. So sometimes they speak about 2 solutions.
Mesos is vaguely related. Mesos came actually out of Berkeley, where I also work, and Mesos has now said they're going to support the Kubernetes APIs. And so I think Mesos has some of the functionality.
I'm not finished my question, excuse me.
Sorry.
But yeah, if we want to deploy like distributed system on a cluster, for example, so it seems possible with Kubernetes because I've seen we can install our worker, for example, in the container and the master and deploy everything like classical cluster, but with the container feature, which is convenient. And would it be possible also, what is the pro and cons if we can use also Mesos to do this? Because I've seen it can deploy stuff like Hadoop and Kafka or this kind of stuff. So which one will you recommend to deploy a big distributed software on a cluster?
Well, I'm a little biased, but I would say the place that Mesos will do clearly better than Kubernetes by itself is for on-prem clusters. Right, so Google's not particularly good at on-prem clusters, except for kind of our own hosted stuff, which is atypical. And so you can use the Kubernetes APIs with Mesos to do container-based deployment. But Mesos will also help you on a bunch of other things, like how do you provision VMs on-prem, right? So in the Kubernetes cloud version, we can kind of magically make VMs whenever we want, right? On-prem, you have to actually have mechanisms for creating VMs, for creating an IP subnet, for putting in firewall rules. And so those kinds of pieces, Mesos is going to be a better bet on that kind of picture of how do you build the cluster on which Kubernetes runs. Right? In the cloud, we give you the cluster. On-prem, you have to kind of do that. So we're working with various groups, OpenShift and VMware and Mesos, to try and figure out what's the on-prem version. Because Kubernetes itself is open source, but it's not sufficient to solve the whole problem. So
maybe one last question here and then coffee break.
Great.
So my takeaway about pod is that it's more like Docker, but with additional stuff like managing shared resources, ports, memory, etc. What am I missing in that picture? What else is it? Or
I would say pod is about grouping containers,
right,
so that they can be moved and managed a bit better. Kubernetes adds, besides pods, the concepts of labels and replication controllers, which are really more about management and operations. And those things are not in Docker. So Docker actually all of Docker really, the core of it is geared towards one node. Kubernetes is fundamentally geared towards a pool of resources that changes dynamically.